Time is 2:30, so let's begin here. Project number 4 is due on Friday at noon. Please note that test number 2 is coming up. It is April 7th. Are there any questions? Okay, we left off on about page 4.8 in the notes. We were talking about this number of cars stopped at the 33rd and Holdridge Street intersection example. And so my data is in stoplight.csv. So for the first time that I was counting the number of cars that were stopped at the intersection during a red light, I had 4 cars. The next time 6 cars, next time 1 car, and so on. I did this for about 40 minutes. Each you can say stoplight cycle in terms of going from red to green, then back to red and green again. Each cycle took about 1 minute. Now, note that there were no vehicles remaining in the intersection for more than 1 stoplight cycle. Why would that be important to know for this example and for what we're going to be doing with the Poisson distribution?
You want to make sure you're not counting the same cars more than once.
Yes, and exactly. Let's also phrase that in a term that we often use in statistics, though. Independence. Yeah. So our observations here are essentially independent. Now, are they really truly independent? Well, you know, what would have happened maybe at 33rd and Cornhusker? You know, maybe some of the cars interacted there, and because of certain interactions there, it caused some dependence in at 33rd and Holdridge. So perhaps they're not exactly independent, but I think it's good enough. So we're okay with independence. Well, what about the Poisson distribution? Can we actually use it? And so one of the things that we know about the Poisson distribution is that the mean is equal to the variance. So let's look at our sample. Is our sample mean equal to the sample variance? And so I took the vehicle's variable out of stoplights, and I simply found mean and variance. And so this is what we get. So the variance is a little bit higher, but not too much higher. I would feel okay with this because I know there's going to be some variation from sample to sample to sample. And, I think, at least with respect to the mean and the variance, it looks like the Poisson distribution assumption is satisfied. But we should go a little bit further. How about we simply look at the relative frequencies for, let's say, 1 car being at the intersection, 2 cars being at the intersection, and so on, and compare that to the true probabilities that you would expect under a Poisson distribution. So what I did then was let me actually go on over here to 10. Oops. Okay. So first of all, I can use a table function with the vehicle's variable. And this is what I do for the sample counts. So once there were 0 cars at the intersection. 5 times there was 1. And now I need to translate that into relative frequencies. So you can think of these as the estimated probabilities. So I simply take, again, the table function divided by my sample size. I put that in an object called rel.freq, just rel.freq. And this is what I get. So 0.025 represents that 2.5% of the time there was 0 cars there. Now let's compare that to what a Poisson distribution would give us if mu is actually equal to the sample mean. Okay? So the first thing I'm going to do is include some additional 0 counts in this relative frequencies. Because of course, anything above 8 should have a relative frequency of 0 for my data. And the reason why I'm doing that will be clear when I then also take a look at the Poisson probabilities. So I'm going to create an object called y. And I'm going to look at Poisson probabilities from 0 to 15. To look at the Poisson probabilities, I can look at d. I can use the function dpois. And we've looked at the d binom function before. It operates the same way. Distribution, Poisson. I want to find the probabilities at values of y. And my mean parameter, is that called mu in the syntax for dpoise? Instead it's called lambda. So lambda equal, and I put the sample mean in there, round everything to a nice set of decimal places. Then let's combine everything in a data frame, and this is what I get. So, for the case of 0 cars, I again observed that happening 2.5% of the time. The estimated probability using a Poisson would be about 0.021, so fairly close. And so you notice that once we get past 9 here, the probabilities are quite small for the Poisson. And so that we could just make that comparison, that's why I added those zeros to the rel.freq column there. Let's look at this graphically. So I'll let you look at the details of the code on your own. But basically what I'm going to do is just graph some bars on a plot where the bar height will be equal to the relative frequency or the probability from the Poisson. The one thing that's new that we've never seen before is type equal h, which again says I want bars on my plot that reach a certain height as given by the y variable. So let me go ahead and do this. So this is what we get. So the Poisson is in black, observed is in red. Again, for 0 cars, remember it was 2.5% of the time I observed 0 cars. The probability from the Poisson was about 0.021. And so what do you think? What do you think about using a Poisson distribution here, given what we observed? There's one place where it's a little bit of a concern, right? That's at 3. But other than that, it's really not too bad. And remember, we only have a sample size of 40 overall, so you wouldn't expect it to be exactly match up. So overall here, I think it's okay to use a Poisson distribution here. I don't have, let's say, extreme evidence saying, no way, this isn't going to work. What would extreme evidence look like? Against using a Poisson. Well, you might have, let's say, the red line shifted way over in comparison to the black, or maybe there might be a lot more variability in where those red lines fall in comparison to the black. Maybe if I had a bunch of red lines up by 15 and 14 and so on, I would be definitely concerned. But here, it doesn't look too bad for a sample size of 40. So, with that then, I'm okay with using a Poisson distribution. So now I can start talking about calculating confidence intervals for the mean using this Poisson distribution. So if you remember, we looked at a number of different intervals last time. Let me see if I could do a split screen here so that we can see some of them. So we looked at a walled confidence interval for the mean. That's what's shown in the bottom split here. And here's my actual code for it. Set alpha, find my sample size, find my mu hat. That's my maximum likelihood estimate. And then use the wall. Mu hat plus or minus the value from a standard normal times the square root of that estimated variance. I get 3.26. So I guess if I wanted to write it out formally, 3.26 is less than mu, is less than 4.49 with 95% confidence. How about some of the other intervals? Well, remember we talked about one that used the log transformation. So there we go. Again, just program that in. I get 3.31 to 4.54, very similar. And then lastly, a score interval, 3.24 to 4.51. at this stage of the course, you should be able to take a formula, be able to program it in. And so that's why I'm not going to go over the formulas of how to do it exactly in detail. What would be interesting to do is that, before you took this class, probably the way that you would approach this was to use the usual old t-distribution interval. So let's make a comparison here. And so I'm going to use t.test to give me my t-distribution interval. I think that was actually included in the intro to our set of notes. And the only thing that's of interest to us here is then the interval that's automatically produced, 3.21 to 4.54, so a little bit wider. And that's what often will happen in these situations. The t-distribution based one will be a little bit wider. And part of the reason is because we have a little bit of a bigger assumption, and that is the Poisson distribution that we're using with these Poisson-based intervals. Okay, so on average, I would expect anywhere from about 3 to 4.5 cars that are in the waiting at that stoplight. Now, by my estimation, it would take probably about 9 cars to block that fire station's driveway, and that was the original purpose of doing this. So on average, we could see that that fire station's driveway is not going to be blocked, because my interval is a lot less than 9. However, I don't think that's necessarily exactly the way that we want to look at it. And maybe what we should do is look at, well, what would be the probability that the driveway is blocked? So in other words, what we might want to look at instead is the probability that y is greater than or equal to 9. Now, using the complement, we know that that's equal to 1 minus the probability y is less than or equal to 8. Why do I want to do that? Well, because I know there's a function called p-poise, for probability Poisson, that essentially finds this cumulative probability. And I can accumulate the probabilities up to 8. So p-poise works very similar to p-chi-sq, similar to p-norm. So the quantile is 8. My mu parameter, which R calls lambda, let's set that equal to what it's estimated to be, mu dot hat. Then 1 minus this probability, and I get 0.0178. So this is equal to the estimated probability that y is greater than 9. So that's why I put a little hat on top of the probability. It's not necessarily a standard notation, but I think you get the point. So we can see that the probability that the driveway will be blocked is quite small. Not 0, but quite small. But I think we also have to think of it from the point of view of this is from one stoplight cycle. There's going to be about 60 in an hour. And we know that the number of cars does vary. So how about we go ahead and look at this from even a different perspective? What's the probability that that the drive will be blocked at least once in that hour period of time? After all, it only takes once for a fire truck to have issues. And if that driveway is blocked, what's the fire truck going to do? Drive over the car? Probably not. But still, if you think of from the perspective the fire truck needs to get out, you don't want this to happen at all. So when you do that, you basically turn this Poisson problem actually into a kind of a binomial problem. Depending upon what kind of stat courses you've had before this, in it like an 801 setting, you may talk about this or you may not. And so since there's one cycle per minute, so like 30 seconds it will be red, 30 seconds it will be green at the Holdridge intersection. Let's look at n equals 60 for the number of trials for a binomial. I'm going to set my corresponding probability, success probability, equal to what is estimated to be then let's let W then count how many times that this driveway will be blocked. I'm sorry, the driveway will be blocked in a 60-minute period of time. So I want, what's the probability W is greater than or equal to 1? Or equivalently, again, use the complement, 1 minus the probability W is equal to 0. So we could find that probability really easy using D binom. So there's 0, there's N, there's that probability, and I get 0.66. That's a fairly high probability. So the probability that this driveway is blocked, or the estimated probability that this driveway is blocked in a 1 hour period of time, 66%. Now, I'm not an expert in various transportation issues. I don't work for the city government either. But I know if I see, but at least from my perspective, if I saw that, I could see that there's an issue there. And I would hope that there might be some way to take care of it. I don't know, maybe the firefighters, whenever the fire truck's getting ready to go, they have I know in other situations this is possible, you know, they have a way to communicate with the stoplights to have the stoplights change so that they can get through an intersection. So maybe they could, you know, push a button, let's say, and whenever there's an alarm that goes off and they have to leave, they push the button, and then that allows the traffic to flow more smoothly. I don't know if that actually happens, but you can see if it doesn't happen, that will be one potential, maybe cheaper way to solve the problem other than move the fire station. Okay, so I collected this data about 3 or 4 o'clock in the afternoon. What do you think is going to happen to this probability during rush hour? Yeah, it'd probably go up. Okay. So I think all of you agree with me that mu is maybe a function of the time of the day. So how could we take that into account in a Poisson setting here?
Include a variable that has the amount of gas during rush hour versus non-rush hour.
Include a variable for what?
For time of day.
For time of day. So maybe if our mean is going to vary as a function of the time of day, maybe you could somehow do something simple like this. Mu is equal to beta 0 plus beta 1 times time. Right? Depending upon how you define time. But you get the point. So in other words, what we're talking about now is a Poisson regression model. So we will talk about that more closely very soon here. Now again, this probability here is a estimate. And so if it's an estimate, then you might want to know what's the true probability. In other words, maybe find like a 95% confidence interval for the true probability. You could do that. You could use the delta method, which we talked about a little bit last time, and it's come up a number of times before, to come up with an estimated variance for this estimated probability, and then find a wall-like interval for it. You're not responsible for it, but I actually did that. You could see I have an additional program called Stoplight _ I think it's called additional, or Stoplight additional.r. You can download it from my website. That shows the details of how you could do that using a function in R called delta method. And the interval ends up being 0.33 to 0.99. So it is quite wide, quite wide. How could you make it less wide? You can reduce the confidence level, but do you like to have less confidence? What will be the other way? What's the standard way for an interval if you want the interval to be, narrower? Take a larger sample size. Yeah, I mean, I only did this for 40 times. You know? So just take a larger sample size, and hopefully the interval will be more narrow. Now lastly, before we move on to the next section, so we talked about 3 confidence intervals for mu. And as I briefly mentioned to you before, there are actually 2 other ones that my book talk about. One's an exact interval. Don't worry about it, but it doesn't hurt to read it and see what it is in the book. And the other one's a profile likelihood ratio. The other one is a likelihood ratio interval. Make sure that you do investigate that. There is a homework problem about that. And it's easier to introduce the profile likelihood ratio interval once we do Poisson regression models. So after we do the Poisson regression models, take a look at that homework, and you are responsible for that. Okay, so let's go to section 4.2 then. So we're going to talk about Poisson regression. We've looked at logistic regression, we looked at multinomial regression, we looked at other kinds of regression models before. The key thing is that you're going to set a particular parameter to be a function of some explanatory variables. And there's going to be some additional parameters inside this function, and we're going to need to estimate it through some data. So as we just got done talking about, maybe you could use a model such as this. Mu is equal to beta 0 plus beta 1 times x. So mu is the Poisson mean parameter. Now there's a problem though with using something as simple as that. And that is, depending upon what beta 0, beta 1, and x are, you could actually have a negative value for mu. Now remember, mu is supposed to be greater than 0. After all, it's a mean count. That's what's representing. You can't have a -1 mean count. -1 people standing in a line, -1 cars at the intersection. It doesn't make sense. So we need a fix. And there's a very simple fix. Use a transformation, just like what we did first with logistic regression models. We use that fancy e to some raised to some power of 1 plus e raised to some power transformation. Why don't we use a transformation here to guarantee that our parameter of interest is always within the correct range? So we could use log of mu is equal to beta 0 plus beta 1 times x. Or in other words, mu is equal to e raised to the beta 0 plus beta 1 times x. Because I'm using the exponential function, I know for sure mu is going to be greater than 0. There you go. Simple fix. This then, written in 2 different ways, is a Poisson regression model as a function of one explanatory variable. Now, at times, you might want to write this model so that you can emphasize the fact that it's for the ith observation. So of course x is going to change depending upon what the observation is. Mu is going to change depending upon the observation. So I could equivalently write the model like this. This is helpful, for example, when you write out the likelihood function. Now, if there are p explanatory variables, you do what you would expect. You just have this linear combination of betas with p different x's. Now, a Poisson regression model is actually a special case of a generalized linear model. We looked at those in Chapter 2, but just in the context of you have a binary response, where y had a Bernoulli distribution to it. Well, y can have other distributions to it as well. And if y has a Poisson distribution to it, we have a Poisson regression model, where the random component is Poisson, systematic components, the linear combination of the betas with the x's, and then the link function. What links mu to this systematic component, that linear predictor, is the log transformation. So if I have this in the context of a generalized linear model, that means a lot of the stuff that we were just doing in Chapter 2 is going to follow through here. In fact, we're going to use the same function, GLM, to estimate the model. So how do we estimate the model? Well, maximum likelihood estimation. Here's what the likelihood function looks like if you have, let's say, p explanatory variables. We've seen the likelihood function. Excuse me. The likelihood function itself is just the product of a whole bunch of Poisson distributions, one for every observation. Notice how I have an I here. And this is what mu sub I looks like. And so, while you don't see any betas necessarily on the right-hand side of this expression, they're in there, just in terms of the mu sub i's. So to find the maximum likelihood estimates, then using likelihood function, I maximize the likelihood function as a function of the betas. As you might expect, there is no necessarily closed form solution for most problems. So what you're going to do is use numerical iterative methods to find what betas maximize this likelihood function given your data. The easiest way to do this then is to use the GLM function in R, where everything that we did in chapter 2 is going to work out here in terms of the syntax. The one difference is going to be what you do with the family argument. Remember before we used family equal binomial, parentheses, link equal logit, in parentheses. Here we're going to say family equal Poisson, link equal log. The estimated covariance matrix for the parameter estimators follows through from exactly what we've done before. Again, it just comes about through using the second derivative, the log likelihood function, find the expected value of it, take a negative, invert it, evaluate the parameter estimates. What function R do you think is going to allow us to get that estimated covariance matrix easy? VCOV. Okay. We can do wall, we can do likelihood ratio based intervals, or inference based procedures, just like what we've done before. So let's take a look at an example. So this example deals with horseshoe crabs and satellites. This is one of my more favorite examples. It's actually, I focus on a different example in my book, but I do have this as an exercise in my book. The reason why I don't focus on it a whole lot in my book is because this actually comes out of Alan Agresti's categorical data analysis books, and I didn't want to do exactly the same thing as him. But it's a good example, so that's why I still like to use it in class. And so what we're going to be interested in is this. These horseshoe crabs, they're out on the East Coast and around about Delaware or so. And at some point during the year, they'll come to shore, and they want to have babies. And so the males are called the satellites, are the satellites, and they gather around a female in the hope of fertilizing her eggs. And so, a few years ago, I was watching PBS. And all of a sudden, I see that it's a show about horseshoe crabs. And so I quickly hit record on my computer, and I got this like 1 minute segment that I'm going to show you here of some information about these horseshoe crabs. And you're going to see what the satellites look like and how they go around the female. So let's take a look at this short video.
Horseshoe crabs prefer spawning in the cover of night, but this is the height of their short season. It only lasts a few weeks. They come to shore when the tides are highest to lay their eggs deep in the sand. Swarmed by hopeful males, the female digs down to bury her.
Okay, so if you see where my mouse is, this is a female here. And we have 1, 2, 3, 4, 5, 6, 7, 8. It's a count. Hopeful males. We have 8 satellites here. And so, you might be wondering, well, why are 8 interested in this one, this female? And what characteristic about her, makes them so interested in her? Let's keep on going.
Her clutch. The males are smaller than the females, but they have a special claw that hooks onto her shell. since fertilization is external, even unattached male.
Okay, so now this female has only 5. You know, is there a certain characteristic about her that makes her, let's say, less interesting? You know, and so what we might be interested in doing is, well, modeling what on average would we expect the number of satellites to be, given some explanatory variables such as, let's say, maybe what we will focus on here, the width of her shell, maybe. But, you know, there's other explanatory variables that we're not going to look at that are possible as well, that are available actually in Aggressi's original data set.
Will father some of the eggs. When her clutch is finally laid, the female breaks through the sand.
Okay, so there's a short video. If you want to know more about horseshoe crabs, obviously I gave you some information in the notes, but here's a nice little story on horseshoe crabs. They're actually quite useful in terms of their blood is used in medical applications to help humans' own blood clot. And so, so what they actually do is that they'll, what people will do is, or I should say people who are in the medical area will do is they'll get these horseshoe crabs and they'll put them in some, this kind of sounds bad, some devices, and they'll bleed them to get their blood. And I guess at least at the moment there's not necessarily any kind of artificial way to reproduce the exact same stuff that's in their blood that these medical people want. Okay, so this is what our model is going to look like. First of all, I guess y is the number of satellites, so mu is the expected number of satellites, so the mean satellites. And we're going to set that equal to a function of the shell width of the female. So the data itself is in a ASCII text, plain ASCII text file. It is actually space delimited, not comma delimited like we've talked about so many times before. So I use read.table here. Here's where the file is. And I say header equal true because the first row of the data set actually contains the variable names. And this is what it looks like. So for the first female, the width of her shell was 28.3 centimeters, and there were 8 satellites around her. So to estimate the model then, again I use GLM, response satellite, explanatory variable width, data's in crab, and here's the new family argument value, Poisson link equal log. Put the results into mod.fit, and then I summarize it. Here's what we get. If you notice, the output looks very similar to what we've had in the past. So here, for example, is beta hat 0. Here is beta hat 1. Here is the square root of the estimated variance of beta hat 1. So from this then, we can come up with the estimated Poisson regression model. So mu hat, of course I need to put a hat on top of mu. If there's no hat there, and it doesn't make sense because this is now for the estimated model. And I just put in, again, beta hat 0, beta hat 1. Of course, we could rewrite the model like this so that we just have log of mu hat on the left-hand side, and then we have the linear predictor on the right-hand side. Okay, so what happens to the estimated mean number of satellites as the width increases? Excuse me? So as width increases, what happens to the mean number of satellites? It increases as well. So what type of female crabs do male crabs prefer? The wide ones, the kind of a wide backside, you could say, which kind of reminds you of a Sir Mix-a-Lot song, if you know what I'm talking about. If you don't, Google Sir Mix-a-Lot, and you'll see what I'm talking about. I'm not going to Google it, though, here, because I'm recording. So of course, though, you wonder, okay, well, that's what the sample says. Well, is there actually sufficient evidence to indicate that? Well, take a look back at the output. We can do a quick check of that. There's my wall test statistic, 8.2. P-value is extremely small, so yes, there is sufficient evidence. Okay. So, you know, a lot of the stuff that we want to do then with this model is very similar to what we've done in the past. So, similar to what we did with the multinomial regression model, I'm simply, you know, going to have some questions here and ask you, well, how would we do this? We actually just did number 1 here, perform a wall test. How can we perform a likelihood ratio test for width, or corresponding for the parameter corresponding to width? What would we do? What function R? One of the ANOVAs, for example. So let's actually go ahead and do that in my program. So I can use the car package to do capital ANOVA. And so I say capital ANOVA mod.fit test equal LR. This is what I get. My negative 2 log lambda statistic is 64.9. P-value is extremely small. So yes, there is sufficient evidence to indicate that width is important. In my program itself, I talk about how you can use the little ANOVA function. And I also do what you could say is somewhat by hand calculations here, where I fit a null model, I fit an alternative model, and actually extract the residual deviances and test it that way, similar to what we talked about in Chapter 2. So how can we estimate then the expected number of satellites when the shell width is 23? Well, just use the model. Mu hat is equal to, again, e to the beta hat 0 plus beta hat 1 times, then here's my x, 23. If you do the math, you get 1.6. So what function R would we use to do this automatically for us? Predict function, exactly. So if we take a quick look at that, I can say predict object equal mod.fit, new data equal. This is where I can put a new data frame here, and I say width equal 23. The type of value that I want produce is response, meaning I want an estimate for the mean. And if I do that, I get 1.6 again. Well, how can we find a confidence interval, a wall confidence interval for mu? So what would be the first thing I would want to write? Mu hat plus or minus, yep, the z value times, yep. So that would be a walled interval. You know, one could get then that estimated variance from the predict function. Remember how we did it in R? Use SE equal true. I'll show how to do that in my program. But is there a potential problem here? Yes. This interval, the lower bound, could potentially be less than 0. So notice you're not restraining at all. So instead, similar to what we did with the logistic regression model, we want to first find an interval for, you can say, beta 0 plus beta 1 times x, that linear predictor. First find an interval for that, and then use the exponential function to find an interval for mu itself. So what I'm going to do first, find the interval for beta 0 plus beta 1 times x, or equivalently, find an interval for log of mu. This is going to be a walled interval. And then use the exp function with it to now put it back, you can say, on the mu scale versus the log mu scale. That is a better interval to use. Now, in actual application, the problems that we faced with logistic regression in terms of the interval maybe potentially being outside the 0 to 1 range, those kinds of problems don't usually happen as often with Poisson regression unless, of course, the true value of mu is close to 0. So how can we do this interval then in R? Well, to help you out, let's see. we go. Wait, back up. Okay, so here's my predict function. Everything was the same as before, but now I say type equal link, SE equal true. And so what that's going to give me, and I'll show you, is some information that I could use for a walled interval for the log of mu. So log of mu hat at width equal 23 is 0.468. There's the estimated variance of, the square root of the estimated variance of log of mu hat. So we can put this all together to find a confidence interval for the log of mu. And then I use the exp function with that to find a confidence interval for mu itself. So let me go ahead and do that. And I get 1.33 to 1.92. There's my confidence interval for mu. Well, how about a profile likelihood ratio confidence interval? Well, I can go back to using MC profile like we did in chapter 2. And again, I'm looking at a confidence interval for log of mu, or beta 0 plus beta 1 times x. Here, in this particular case, I have, you could say, a coefficient of 1 on beta 0. And then for x, that's 23. So I set up a matrix where this is the corresponding element for beta 0, corresponding coefficient on beta 1. Put that into a matrix called K. Then I use MC profile with the information from fitting the Poisson regression model. CM equal K. Coefficients matrix equal K. Yes?
Why did you choose 23?
No particular reason. Sorry. It was up here. I just to say, okay, well, let's say we had a shell width of 23. Let's do some calculations. And so that's where it started at 3, and I just kind of carried forward with other 23. Sorry, obviously that's not necessarily clear for 4 and 5 there. So I put then a whole bunch of information about -2 log lambdas into an object called linear.combo. Then combined with the confidence function, I'm able to find a confidence interval for log of mu. Or equivalently beta 0 plus beta 1 times x. Then combined with the exp function, now I have my confidence interval for mu itself. It's just about the same as it was for the wall. So question number 6 we've actually already answered. Use the vcove function. And let's say you want to include some type of transformation of an explanatory variable in the model. Let's say I want an x squared. What would I do? Use that I function with it. If I want interactions, I could use like a colon to get an interaction between 2 explanatory variables. Okay, good. Well, let's look at a plot of our model. So first thing I'm going to do is do a scatter plot of my data and then plot the model on top of it. So for my x-axis, I'm going to put the width of the crab. The y-axis, I'm going to put the number of satellites. Note that I don't think we've seen this before, the /n. Does that look familiar at all? Okay. That's a little, you could say, little trick in R, so that if I go down here to the plot here, that allows me in any kind of text to put more than one line. So that /n, which is on page 23, correspond to my main title of my plot. I say, first of all, horseshoe crab dataset /n with Poisson regression model fit. So everything after /n goes down to a second line. So it's just a little trick. that /n actually corresponds to what's called an escape character. And you'll see escape characters in various other settings, and this is one. Okay. Now to plot the actual model, just like what we did with logistic regression, I'm going to use the curve function. So I use curve. My expression is, well, e raised to my beta hat 0 plus beta hat 1 times x. Remember what curve does? It's going to put 101 equally spaced values into the expression and then plot those. Add equal true, add it to the current plot. And I plot it in red. So the red line there represents the actual estimated model. Well, what about those confidence interval bands? Well, to help you out, and you might want to do this, use this function in other settings as well, I've written a function called ci.mu that basically uses the same techniques that we had just seen a few minutes ago in my program to find a confidence interval for mu. So in this function, I'm going to pass in my x values that I want to predict at, my model fit object from GLM, and then whatever I want for alpha to be. First, I estimate the linear predictor part. Then I find the lower bound, upper bound, and I return the results back as a list. This function is very similar to a function called ci.pi that I had written in chapter 2 that we had talked about. So to test this function out, I say new data equal data.frame width equal 23. So I'm going to get an interval at x equal 23. My model fit information is in mod.fit. I want a 95% interval. In return, I get a list that has two components, lower and upper bounds, that include the lower and upper bounds of the interval. Using that information then, I can use the curve function, or using that function, I can use the curve function with it to find or to plot then my confidence interval for mu. And again, this is very similar to what I did in chapter 2. And so the blue lines then represent the 95% confidence interval bands for the true value of mu. Are there any questions? Well, what do you think? Ignore the blue lines for now. What do you think about the fit of this model? You know, what are we looking for to evaluate the fit typically? How close the points are to the red line, right? We see a lot of variability there around that red line, don't we? You know, take into account that y-axis there and what those numerical values mean. So, you know, it's actually a little bit difficult from this kind of a plot to make that judgment. You know, I don't think it's as easy as it is in normal linear regression. And we saw, for example, with logistic regression models, how plots like this could be a little bit misleading. I don't think it's necessarily to that extreme here, but I think we need to remember what we're trying to model. We're trying to model essentially a mean. We're not modeling, you know, y directly. You know, on our left-hand side of our model, we have mu. So maybe a better way to evaluate the fit of this model is to somehow plot mu. Of course, we don't know that though. But maybe what we could do is come up with maybe, let's say, the sample means for ranges of our widths there, and plot those sample means, and look how far the red line is from those sample means to get a general idea of, well, how well is this model fitting? So that's what I'm going to do next. So the first thing I need to do is group the data. I'm going to find 8 different groups of my data based upon the width. Now the groups I'm going to use are, group 1 is going to be widths less than 23.25. Group 2 is going to be greater than or equal to 23.25 but less than 24.25. And then I keep on going in that manner. Why did I choose those? That's because that's what Agresti chose. Could you choose other ones? Yes. We'll talk about that shortly. So there's a number of different ways that you can get your data into groups. This particular way is based upon stuff that we've seen before with the if-else function. So if I say if-else, make a test. Is my width of an observation less than 23.25? If it is, put it into group 1. If it's not, do another if-else. Is my width less than 24.25? If it is, well, then that means it's in group 2. If it's not, then you keep on going. That's one way to put the data into groups. So I combine these groups with my original data set, and then I just print off the first 6 observations. So you can see for group 1, observation 2 falls in that, had a width of 22.5, which was less than 23.25 up there. Now there is other ways to do this. I want to mention it to you. You can look on your own. You're not going to be responsible for it. But in chapter 5, we come back to this horseshoe data set. So there are actually some issues with it. I will talk about in section 5.3. And in the program horseshoe _chapter 5.r, which is on my website, not my book's website, you will see probably an easier way to put this stuff into groups. Surprisingly, I didn't know the existence of this particular function until recently, so that's why you don't see it here. But this works fine, but you can look at that program there to see another way to do it too. Okay, so now that I have my data in groups, what I would like to do is for each group, find what would be the group width mean, and also find the group satellite mean as well. And I'm going to use that to my advantage to try to evaluate the fit of my model graphically. So how can I find these group means? Well, this is where we go back to something from chapter 2 once again. Remember the aggregate function? So we can say aggregate satellite by my groups that I just created, and for each group I want to apply the function mean. Also, for my widths, aggregate by groups, where I'm going to apply the function mean again. So that when I organize everything nicely, my data frame here has the sample mean for every group, for the satellites and also for the widths. So for group 1, the mean number of satellites was 1. The mean width was 22.69. What I like to do then again is compare these means for the number of satellites to what my model suggests should happen. And so I need to plot these sample means. So to plot some points on a plot like what we just did, I can use the points function. I'm going to plot points at the width means and the satellite means. The plotting character I'm going to use is a triangle, which is plotting character number 17. The color is going to be dark green, and I'm going to make it a little bit bigger than the normal default. And this is what I get. So for example, the first green triangle here is drawn at 22.69 and y equal 1. And so what we are trying to do here is look, are the green points close to the red line? If they are, that's kind of an ad hoc way to say, yeah, your model makes sense. It seems like it's doing what it's supposed to be doing. If the green points are not close to the red line, then you might start to worry about the model's fit. So what do you think here? It seems like the red lines going through, roughly speaking, the middle of those points is not perfect. but it seems to be relatively okay. Now, like I said, in section 5.3, we will find a problem with this model. So stay tuned for that. But at least using this ad hoc procedure here, it seems okay. Good question.
Should those triangles be weighted like we did for the logistic regression? Like,
In terms of like the number of observations per. You could do that as well. That would be another component that you could use. Alternatively, what you could do instead is to use a different kind of grouping. And so in this alternative plot here, and you can take a look at the code in my program, what I've done is said, okay, how about we essentially evenly divide the observations into groups. So if I have, I don't remember how many observations I have. It's like something like 150. And so if I want 8 groups, well, let's put about 18 in group 1, about 18 in group 2, 18 in group 3, and so on. And that's what I did here, found the group means, and this is what I get. And you can see in that particular case, we don't get as good of results. And so one of the reasons why I do this alternative here is to show you that this is an ad hoc procedure. It's one that I would typically do, but you've got to realize that depending upon how you put your data in groups, you can have different results. In chapter 5, there are measures called goodness of fit tests. Perhaps you've heard of some of these in other courses. And some of the popular goodness of fit tests are based upon this premise of putting the data into groups and then calculate a simplified statistic that measures, well, basically how far is the green from the red. But depending upon how you put the data into groups, you could potentially get different answers. And so we'll come back to this idea again. I think it's section 5.2. Let's see, did I talk about everything? Yes, I did. Good. So like I said, and sorry if I'm repeating myself, I would do something like this, but I always understand that I get a different result depending upon how I group the data. And I just think of this as one tool that I like to do. And basically I'm looking for warning signs. Is there something going on here that I don't expect? And even if the green dots are close to my red line, I do not necessarily immediately conclude, oh, my model's great. I wouldn't do that. Okay. So let's talk about interpreting this model now. We did a little bit already by looking at, well, what's the sign of this beta hat? If the beta hat is positive, that says as x increases, the expected value for y increases as well. And then if beta hat's negative, that says that as x goes down, if beta hat is negative, as x goes up, the estimated mean goes down. So we've done a little bit, but let's talk about this some more. In chapter 2, what we did was look at odds ratios. In chapter 3, what we did was look at odds ratios. Do you think we're going to look at odds ratios now? No! You can actually with Poisson regression models. We'll probably talk about that a little bit later in this chapter. But instead, we're going to focus on a different measure. But it's going to be very, very similar to looking at odds ratios. So let's consider a model that has just one explanatory variable in it, x. And for emphasis here, for notation, I think this makes it easier for me to introduce stuff. Let's, instead of just calling it mu, let's call it mu of x to emphasize that this is a function of x. Then like what we did in chapter 2, we were often looking at, well, what happens if we increase x by c units? How about we do the same thing here with our Poisson regression model? So now we have mu of x plus c. And what did we do in the odds ratio section? Well, we basically we found two odds of a success. An odds of a success at x plus c, and odds of success at x. And we divided the two. We found a ratio. We're going to do the same thing here now, but for means. So here's my ratio of my two means. So if I plug in then what the model says, look what happens. Beta 0 cancels, x times beta 1 cancels, and you're left with just e to the c times beta 1. Should look very familiar. So it's nice that we have this simplification again, just like in chapter 2. And then I have also occurred in chapter 3. So then what's the interpretation? Well, what I like to do is make the following little change. I'm going to look at a measure called PC for percentage change. You know, we looked at OR for odds ratio before. Now I'm going to look at the percentage change in the mean subject to a C unit increase in X. That PC is going to be 100 times my e to the c times beta 1 minus 1, and then put a little percent sign next to it. So for example, if e raised to the c times beta 1 was equal to 1.1, that means PC is equal to 10%. So as c increases, if c increases by, for a c unit increase in x, I have a 10% increase in the mean. So then this is the formal interpretation. The percentage change in the mean response that results from a c unit change in x is PC. Of course, PC hat would be 100 times e raised to the c times beta 1 hat minus 1, and then put a percent sign there. Okay. So some comments. First of all, this interpretation is not dependent upon the original value of x. Just like what we saw with the basic odds ratios that we were seeing in chapter 2, and also some of them in chapter 3. X falls out. That's why this is a nice way to interpret the effect the response has on the effect the explanatory variable has on the response. Of course, choose an appropriate value of C for your data, just like in chapter 2. So I guess my third bullet I kind of already talked about. That's PC hat. You can use walled and likelihood ratio intervals, as we've done in the past for this. If there was more than one explanatory variable in the model, well, the same results that we have here holds true. You just have to add then in your interpretation, holding the other variables in the model constant. And then lastly, if there's interactions or transformations or maybe even categorical explanatory variables that you have in your model represented by indicator variables, well, we saw in chapter 2 what happens. The same kinds of things happen here. Now, a question on a test might be, okay, why don't you derive PC for a model that has a square term in it, or an interaction term in it, or an explanatory, or a categorical explanatory variable in it. Derive it on a test. So let's go back to the horseshoe crabs as satellites example. I've decided to do C equal 1. Well, that's easy. It just kind of seems to be intuitive to use for a 1 centimeter increase in the width of the shell. And if I were to do that, my e raised to the c times beta hat 1 power is 1.17. And then if I find PC hat, I get 17.82. So what does this mean? A 1 unit change in width leads to an estimated 17.8% change in the mean number of satellites. Now notice I don't necessarily say a positive or a negative change. I just say a particular change. And so, some people might prefer a little bit alternative wording, something like this. A 1 unit increase in width leads to an estimated 17.8% increase in the mean number of satellites. Or alternatively, the mean number of satellites is estimated to increase by 17.8% for every 1 centimeter increase in the width of the shell. So those interpretations would work fine. It's just helping to emphasize what you're talking about, an increase or decrease or whatever. So, what if C, what would be, let's say you don't know what C should be. 1 seems to be fine in this particular case, but, perhaps, you might be left with a situation where you don't know what to choose for C. And just like what we saw with the weak data set in Chapter 3, what you could do is use a 1 standard deviation increase in your X. So if I were to do that, my standard deviation for width was 2.1. So that leads then to a e raised to the c times beta hat 1 of 41.3. And so a 2.11 centimeter increase in width leads to an estimated 41% increase in the mean number of satellites. Okay. Well, what about a confidence interval for PC? I keep on wanting to say, I keep on thinking PC means politically correct. We're finding intervals for politically correct. We're estimating politically correct. No, percent change. Okay, so when we're using the GLM function itself, what confint does by default is find a profile likelihood ratio interval. So I can use confint here, just like what we did in Chapter 2. Say object equal mod.fit. Parm corresponds to the actual variable name that you see in the output when you say summary mod.fit, and that's width. The reason why I emphasize that is, remember what happens when you have a categorical explanatory variable in your model. Indicator variables are formed, and you need to know, well, what is R calling that indicator variable, and that's what you put in here for the parm argument. That will happen in your next project. Level equal 0.95. And so then if I find the interval for PC itself, I take 100 times e raised to the beta dot ci and subtract off 1, and I get 13.28 to 22.51. So with 95% confidence, a 1 unit increase in width leads to a 13% to 23% increase in the mean number of satellites. Okay, you could also use the MC profile package as well, and so I've just put that in here since it's, we haven't used it since Chapter 2, just as a reminder of how to do this. Now remember that the MC profile package would be the preferred way to do this if you have some kind of model that has, let's say, interaction terms in it, if it had quadratic terms in it as well. And in fact, if you have a categorical explanatory variable, often writing a big K matrix will be often the preferred way to do this. So please remember that. Also, you could do a walled confidence interval with MC profile using the walled function. Speaking of walled confidence intervals, here what we could also do is use the confident.default function as well. And works very similarly to what we've seen in the past, and in fact the interval is very similar as well. And I guess also for emphasis on page 33, I show you, well, what you could do without confident or MC profile. You could do this all essentially using by-hand formulas, which you are responsible for. Are there any questions? Okay, let's move on along. Page 34. Let's say you do have categorical explanatory variables in your model. How do you take those into account? Same as we've done in the past. So if we had a categorical explanatory variable of 4 different levels, A, B, C, and D, of course you're going to have 3 indicator variables for it. You represent them in the model as shown here. So x1 represents the level B, x2 represents the level C, and x3 represents the level D. Let's just put that there. Now again, you have to be careful about, well, if I were to take e to the beta 1, what does that mean? It's not comparing level B to all the other levels. It's actually comparing level B to level A, because A is the base level. We saw that in chapter 2. If I wanted to compare, let's say, level B to C, then I can use e to the beta 1 minus beta 2. Again, you're just taking the ratio of two means. And maybe I don't need to go over that, but we have a section in our book on it, so that's why I decided to bring it up again. Page 35. Okay. So with respect to contingency tables, Poisson regression models are very useful. Now, in terms of the Larry Bird example, well, we looked at two different ways that you can think about how these counts can come about. So the first way is that the row 1 represents a binomial distribution. The counts come from a binomial. Row 2 represents the counts come from a binomial. And in chapter 3 we said, well, how about all 4 of those counts come from one multinomial? Chapter 4 says, well, now what you could do is think of each of these counts as Poisson independent counts. And you can find a Poisson regression model where both first and second are explanatory variables used to model these counts. Okay, let's talk about how we can do that. Let me see here. Actually, this, given the time here and how long it will take me to get through this example, might be a good place to stop. I do want to mention, though, we've talked about now 3 ways that the counts of a contingency table can come about. Independent binomial or equivalent independent multinomials for each row. One multinomial, and then essentially I times j Poisson. There's actually a 4th way. Does anyone want to venture a guess what that could be? How you can think of how the counts of a contingency table come about? Excuse me? You said what? Well, Bernoulli's basically taken into account with the binomial. If you've had Stat 882, this follows from what you would learn in that course. Excuse me? I can't hear you. I'm sorry.
Exponential?
No, sorry.
Negative binomial?
Well, geometric's just a special case of negative binomial. I never really thought about that. Not normal. I wasn't thinking of negative binomial. I could see potentially it could be. So, but let's think of another distribution then.
Uniform?
What's that?
Uniform?
Nope. This is a distribution that is for a discrete random variable. Log normal is continuous. Excuse me? Gamma's for a continuous random variable. It has to be for a discrete random variable. First letter is H. Hypergeometric, exactly. So in section 6.2, I talk about that. We may get to it. We'll see. What you can do is think of the row counts and also the column counts as fixed constants. And then there's only one random variable that's left in these 4 cells. It's one, just pick one, doesn't matter which one. And if you think of maybe often what's done is that one's thought as the random variable, that one has a hypergeometric distribution. If you have a larger contingency table, maybe I by j, you have what's called a multiple hypergeometric distribution. So take a look at section 6.2, and that's the one section I like to get to, if possible, at the very end of the semester. If we have time, we'll talk about it, but we'll just see. Are there any questions? Okay, that's it for today.